Excellent job, Cole. Excellent job, Cole, in the warm-up. An exponent's a large or small number. A log is used in the case when we have an exponentially large or small number. So that's when we use it. And what is it then? What is it? Shorthand? Shorthand abbreviation for an exponentially large or small number? Because we don't look at the mantissa, we look at the what of that number. If we all agree upon a common base, like base 10 in your science class, scientific notation, base 10, the common log is base 10, we'll talk about that, or base 3 or base 5, whatever common base we all agree on. Then to talk about this exponentially large or small numbers, we can refer exclusively to the what? The exponent. Yeah, there you go. So remember, I said to never forget to remember that at the basic level, an exponent and a log are the same, right? The log is an exponent, and an exponent is a log. They are what? Mathematical, not cinnamon. Cinnamon. Take the cinnamon challenge. Don't do that. They're mathematical synonyms. Yeah, they're replaceable with each other. But a log is not just any old exponent. It's a very special exponent. It is the exponent to which you must raise that agreed upon base to achieve whatever desired result you're trying to obtain. Okay. So I'm not going to write that down, but it would be something like this: blah 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 exponent, right? Blah 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 blah. Yeah, that's good enough. All right. So we talked about being able to go back and forth between exponentials and logarithms. And for lack of a better definition, I call this the conversion formula. Okay. It's just sentence structure, right? When I get sad, I do math. I do math when I get sad. It's the same thing. It's just structured differently. So this is a theorem, right? And the double-headed arrow, of course, means that it works both ways. It's an if and only if statement, which we abbreviate IFF. So there's a lot of mathematical jargon here. So if and only if just means you can put an if on the left and a then on the right. So you can read it like this, if then, or you can read it like this, if then, and read it backwards. Let's go try it both ways. All right. If log base b of x equals y, then b to the y equals x. That's true. All right. Or you can read it the other way. If b to the y equals x, then log base b of x equals y. It's the exact same thing. We talked about going around the world, converting from one to the other. If you have a log, b is the base. So b to the yth power, the log is the exponent, equals the x. And what do we call this x behind the log? We called it the base is b, but the thing that we actually take the log of is the argument. Yeah, we wrote that up above. Good. Fire today, Natalia. Be careful in the back of your hair. All right, she's on fire. Might be like Michael Jackson filming a Pepsi commercial. Y'all get that? Yeah, that happened. Okay. I told y'all that I would prefer that you don't memorize the gimmick. Like Brady said something like, I just like switch things out and then I let the log drift away or something like that, float away. I don't know.
I just need to move the B down.
Okay.
No, I just moved the base down when I switched the X to Y.
And then what happened to the log? You said something creative. It like it disintegrated. Yeah, floats away. Okay. What'd you say?
Make a table out.
You make a table out of the log. All right. Don't waste wood. Don't waste fun either. So we did come up with this little idea here too, right? That logs and exponents are what's of each other? They're inverses of each other, right? They're inverses of each other. So here's how I would prefer you're able to go back and forth from one to the other. Let's look at multiplication real quick. If I have 5 times x equals 7, right? And I want to undo multiplying by 5 so I can solve for x, what do I do to both sides? I divide both sides by 5, and I could show that like this and like that. And of course, these divide out when you get x equals 7/5. That's like basic algebra 1, bless you. Now that works because division undoes multiplication. Okay, same thing with addition and subtraction. But now we have this team, this duo, exponentiation and logs. So here's what we could do. And I'm just going to squeeze this in. Let's say we have log base b of x equals y. And you want to solve for x, okay? Well, what's sitting there in front of x? Log base b, right? Log base b. So just like when we had a 5 times x, we had to undo the multiplication by dividing by 5. Here we have to undo logging base b. Guess how you undo logging base b? No, you can't divide because division is not the inverse of logging. Exponentiation is what it's called. Exponentiation. So here's what you can do. Go ahead and copy this. This is kind of nice. We could do this because we're going to show the sequence. What you do is you raise both, you exponentiate both sides. Move this little equal sign down now. Okay. So what happens now is log base b to the x is the exponent on the left and y is the exponent on the right. Now, what happens when you compose two inverse functions back to back? Undo each other, right? 2 steps to y'all's left, 2 steps to y'all's right. I'm back where I started. So guess what we're going to get on the left? If I log base b and exponentiate base b, I'm back to plain old. Yeah, they undo each other, right? It's just like when we divided by 5. They divided out, we got 1x. Same thing here. If I have log base b and I exponentiate both sides base b, they undo each other and I get x equals b to the y. Well, isn't x equals b to the y what we have here? It sure is, okay? So that's the algebraic way to go back and forth between them. All right, now what if we start with x equals b to the y and I want to solve for y? Well, if I want to solve for y, I have a base here, b. How do I undo this exponentiation? What's the inverse of exponentiation? Logging, right? Logarithmicking, whatever you call it. So here's what you do. You have to put the log in front on both sides. It's an operation. So we have log of x and then log of b to the y. It's a little bit different, right? The exponentiation makes those things exponents, but the log goes in front and now they become arguments. So on this side, I have log of x equals, oh, and this is what, I'm sorry, I forgot what, log base b. Oops, my bad. That was my fault. The inverse of exponentiating base b is logging base b. So that's what we do. We log both sides base b. And guess what happens on the right-hand side? Guess what happens when you compose two inverse functions back to back? They undo each other, right? Yeah, and we're left with what we started. So we get that. And is that the same as this over here? Yeah. So that's another way to go back and forth between those two sentence structures, okay? And I don't care how you do that. Algebraically is nice because it's a technique, right? Like when we solve for x by dividing both sides by 5. The point is you have to know that those two are the same. I mentioned on Friday that if we just really understand what's going on, we can convert it in our heads, right? You can do the around the world thing on the left, but if you're starting with the exponential, you're like, okay, b is the base. We call it the base in both of them, so it's easy to remember. And then the log is the exponent. The log is the exponent. What's the exponent? Y, right? See y right here? It's the exponent. So then the log is y. It's the exponent. And there's only one other place for x. It's the argument. So you got to understand logs on all of these different levels now before we even proceed. Because the thing that most students hate about logs is because there's so many synonyms. Logs are giant killers. They make molehills out of mountains, as you're going to see here soon enough in the next section. There's a lot of properties that make logs very useful, right? Goes back to what Cole said. When we have astronomically large numbers, they make them manageably small. We have microscopically small numbers, they make them manageably big, okay? All right, so now that we understand logs, let's go ahead and it says to solve for x in each of the following. Solve for x in each of the following. Well, look, part A. It's kind of misleading, isn't it? It's already solved for x, right? In fact, if I flip it around, x equals log base 3 of 27. So you could stop here. This is an exact answer. So if this were like a free response, you could stop there. But what if this were a multiple choice question? I might ask you a better instruction here might be to simplify x, okay, since it's already solved for x. In other words, log base 3 of 27. If I convert it to exponential, that would be 3 to the x equals 27, right? 3 to the x equals 27. That wouldn't be solved for x anymore. So my question is then, is log base 3 of 27 equal to a different number? The log is the exponent. So x is the exponent, right? The log is the x is the exponent to which we must raise 3, the base, to get the desired number of 27. In other words, 3 to what power is 27? 3. That's how you have to think about it, right? The log is the exponent. So do the conversion in your head. If you want, you could do that. You just ask yourself in your head, right? 3 to what power is 27? 3 to what power is 27? So those are the exact same numbers. 3 is equal to log base 3 of 27. Okay? So if you're in basketball and you shoot a basket from behind the line like Steph Curry is now the all-time leader in log base 3 of 27 pointers. If you're into that, that's the same as 3-pointers, right? So when you make a 3, they run off and they do this, right? How do you make the log base 327 symbol with your hands? I don't know, but you could, right? And everybody at home be like, dude, that guy is very mathy. Like David Robinson, he graduated from the Naval Academy, went on to play for the Spurs, Hall of Famer. He was a math major at the Naval Academy. How about that? So David Robinson, a few threes that he made, he probably put up the log base 3 of 27 sign. I got to ask him what that was when I see him next.
It was just on the back of his face.
Maybe so. Bless you. Bless you. All right. I want to have you do this one now. Simplify. It's already solved for x, but log base 4 of 1/64 should be equal to, it simplifies. I'm not going to ask you to simplify if it doesn't simplify down to a nice rational number, either an integer or a fraction. Go.
I got it.
Negative. What'd you get?
-3.
-3. You got -4. -3, -4. Do I get a -5? Do I hear a -5? We'll see if anyone can confirm either one of those.
I mean, I can probably confirm it right now if I use a calculator.
Yep. You are the calculator, Brady, right now. Confirm it. Go off to the side and work it out.
I mean, I already did that since 4 squared is 16, but if you were to put 4 cubed, then it would equal 64. But to get it into the fractional form that it is, you need to like flip it.
Yeah. And how do you flip a fraction? Yeah. There you go. Did you hear his argument? Yeah. 4 to what power is 1/64? That's what we're looking for. 4 to what power of x? What is x? To get 1/64. Well, 4 to the first is 4. 4 to the second is 16. 4 to the third is 64, right? 16 times 4 is 64. But we need to flip that, and the way we flip a number is we make its exponent negative. So it should be -3. And here's the reason. If you want to, I said to work it out, it's because 4 to the -3rd power equals 1/4 to the 3rd power, which equals 1/64. That's how you check it, right? The point of this is to help you to start thinking in terms of logs, because you probably haven't before. Okay. But now that you got the idea, here we go. Do this one. Simplify x. Ah, I see many of y'all, even though it's already solved for x, which is what I'm asking you to do, I see many of y'all actually converting it. 2 to what power is the square root of 32? That takes it kind of a step away from where we want, right? Because we want to know what x is. But if we're thinking about it in the correct way, we can do this. Exponential functions, remember, are one-to-one. What does a one-to-one function mean? It not only passes the vertical line test, but it also passes the horizontal line test. For every x, there's only one y, and for every y, there's only one x. So if you can write it as exponential, 2 to the what power is the square root of 32, all you got to do is try and manipulate the right-hand side as a power of 2. So let's do that.
I mean, 5 is what makes 2 32.
Ah, so 32 is 2 to the 5th, right? Okay, that's good, because now we got the 2's. And then the square root of a number is the same as raising it to the what power? 1/2. Yeah, we'll go back to like day 2 in this class, remember? And now, when you raise a power to a power, what do? You multiply. 5 times 1/2 is 4 5/2. Yeah, 2.5. So on the left, I have 2 to the x. On the right, I have 2 to the 5/2. Can I then say that x must equal 5/2? That just because the bases are the same, the exponents must be the same? That doesn't generally work. Generally, it doesn't work. But guess what? Since exponential and log functions are one-to-one, because they're one-to-one, it actually does work. Okay? It actually does work because they're one-to-one. Now, watch. You can either just say, oh, I got the bases the same, therefore the exponents must be the same. I call this the GTBTS method, the get the bases the same method. And many of y'all intuitively kind of started by putting it into exponential form, which is nice because we think better in terms of exponents. We've been raised on exponents, if you will, not on logs. But if you have an exponential function and the bases are exactly the same, you can drop the bases and equate the exponents. And it's only because they're one-to-one. Now, there's an algebraic way to do it as well. Let's think about the algebra that we just talked about. If I really want to now solve back for x, I want to solve for x again, because that's what I have to do. The exponential format was just an intermediate form to help me to solve it. If I want to solve for x and currently it's base 2 exponential, how do I undo exponential base 2? What's the inverse of exponentiation base 2? Logging base 2, for lack of a bit, logging base 2. So just like I showed you, let's go ahead and put log base 2 in front of both sides. Okay, and what's going to happen? What is log base 2 of 2 to the x? It's x. And guess what log base 2 of 2 to the 5/2 is? It's 5/2. For the same reason the left side is x, the right side is 5/2. So that would be the algebraic way to do it. So we now have 3 different ways to do these types of problems, right? We can do them intuitively. Just tell ourselves 2 to the what power is the argument. That works nice for something like this, yeah? 3 to the what power is 27. It's a really nice power of 27. But if it turns out to be an argument that's a little bit more sophisticated, we can actually convert it. Like over here, we could have gone 4 to the x is 1 over 64. And now if I can write 64 as a power of 4, which again, I'm going to give it to you knowing that you can, now you're like, oh, I can just bring this to the top and it becomes 4 to the -3rd. And now did I get the bases the same? I did. So you can either log both sides base 4 or just say x must equal -3. So we have an algebraic way to do it. And or that's still the intuitive way to get the bases the same. But then we have this more formal method, algebraically undoing the other side. 3 different ways to do it. How do you feel about logs so far? You want to build yourself a log cabin? Surround yourself with logarithms? Cozy.
Either going to be a really big or a really small packet, right?
Yes. Yes. Because that's what logs do. Yeah. Okay. So here's the fact that I just told you. Since b to the x and it turns out it's inverse, which we'll look at the graph of that later, are both 1-to-1. If b to the x equals b to the y, then x must equal y. That's what I call get the bases the same. It's a consequence. It's kind of like a theorem. You don't have to show the algebraic technique, right? And it works with logs as well. So if you have log base b of x and log base b of y, since logs are 1-to-1, you can equate their arguments. X must equal y. It's kind of the same thing. That's the get the bases the same method, GTBTS. All right. Additional fact. The previous fact is in a box while this one is not. Boy, that would have been useful last Tuesday, right? On National Trivia Day. Okay. There are two bases really that we're going to be looking at primarily. Your calculator, your TI-84s are pre-programmed. The first one is base 10, and base 10 is called the common base or the common log. All right. It's the one that the scientists use. It's metric. Yeah. We have 10 fingers, 10 toes, most of us. So 10 is a really nice base. It's easy to look at powers of 10. You just add zeros. So that makes sense, right? So we do kind of still use a little bit of metric carryover. It's so common then that when you're writing it, you don't need to show the subscript. So if you just see log of x, that's how you read that, log of x, and you don't see a subscript, if you don't see a base, but you see the 3 letters log, it's implied to be base 10. Okay. Is it okay to still write it with log base 10 showing? Yes. That's fine. Yeah, you can. For extra clarification for your own or others, it's fine. It's better to have it, not need it, than to need it, not have it.
My dad uses all the time.
What?
The same my dad uses all the time.
Oh, you?
Better to have it and not need it than need to not have it.
He says that all the time? So do I. I say that all the time too.
Better to have an umbrella in case of rain than to not have an umbrella and it does rain.
Right, right. Same with a hole in your head, right? It's better to have a hole in your head and not need one. No. I usually, yeah, umbrellas are good. I usually say it about parentheses, right? Grouping symbols. Better to have them and not need them than to need them, not have them. But yeah, if you don't see the subscript, tell your dad that he and I think alike in that respect. Yeah. That's the common log. Now, mathematicians, we like the scientists. They take our stuff and they use it. And we're like, okay, whatever. We like the natural base. The natural base. Being natural, it's a lot healthier too, right? It's all natural. It occurs in nature. Like if you've ever stared at a pineapple and you follow kind of the swirls on the exterior, it follows a pattern that really is Fibonacci. And it turns out that E, the natural base, is related to the Fibonacci sequence. Okay, so it's beautiful. And in Latin, we've already talked about Latin today, right? Alia iacta est. The bar has been set. What did we say? No, it's not the bar has been set. The die has been cast, right? Logarithmus naturalis. It's a beautiful word. Naturalis. So in Latin, log comes second. Oh, thanks, Adobe. I've been waiting for this update reminder for such a long time. No, I don't want that. Go away. So when we use base E, and of course, everyone knows what base E is. We've talked about it, right? It's 2.718 ... It's an irrational number like pi. We call it a transcendental irrational number. Pi is another transcendental irrational number. Square root of 2, the one that got Hippasus killed, it's called an algebraic irrational number. It actually has a number in it, not a letter. It comes from an algebraic equation. This is where we get the ln, okay? And we've seen this. So if you see ln of x, and that's how you read that, the natural log of x. Natural log, ln is natural log backwards, right? The natural log of x, that is the same as log base E. Is it okay to write it on either way?
Yes.
Yes, but get in the habit of writing it like the left side, because it's streamlined and we tend to use it. But if you want extra clarification, the goal of what we're trying to do here is not just learn math, but really learn how to communicate. I usually write LN in cursive just because it does flow easier. And the L, when you're writing it by yourself, can look like a 1, right? So you don't want to get it confused with 1 times n. So if you write it like that with a little curly QL, it's kind of fun. Natural log of x is base e. All right, Euler's number. That's where we get the letter E, Leonard Euler. Leonard Euler, E-U-L-E-R. All right, it actually comes from this. This is where there's lots of different applications. It's the limit as n goes to infinity of 1 plus 1 over n to the nth power. That happens to equal E. It's pretty cool. Okay, yeah. And this formula right here that we're taking the limit of as n goes to infinity, it's the formula for compound interest, right? And we talked about compound interest. Compound interest was like when we earned 5% in our bank account every year. That's exponential growth, right? Well, sometimes instead of compounding like once a year, maybe they compound it twice a year, or maybe they compound it daily, right? So like when you're taking out a loan, and this is good life advice, when you're borrowing money, or sorry, when you have money in the bank will pay you interest and they'll compound it regularly, maybe once a week, maybe once a month. But if you're borrowing money from like a credit card company, they compound it daily, sometimes twice daily. Now, what's the difference? The more you compound the money, that is, the more often you go in, see what the balance is, and then calculate the interest on it and add it back to it. The more often you do that, the faster it grows, right? The faster it grows. So when you owe money, just realize that interest rates are usually higher and it's compounded more often. Those credit card companies, they want your money. But when you're offering your money to someone to store for you, it'll be a lower rate. It'll be compounded less often. This is what happens when you compound, not every hour, not every minute, not every second. N is the number of times it's compounded. We're compounding it. It's called continuously. Is it physically possible to continuously compound something? No, physically you can't, because as soon as you start to calculate the interest, you've missed all the time in between those two calculations. But when you do it mathematically, it turns out that the base, the interest rate, if you will, turns out to be E, 2.718, which is 117% constantly added to your money. Isn't that fascinating? That is fat. And that's related to the spirals on a pineapple or the spiral in a nautilus shell. They're all related. It occurs in nature, a natural base. Money occurs in nature. Yeah, absolutely. I think rocks were probably the very first money that caveman used as commerce, right? Here, have this rock. Thank you. Right? That's right. And now you owe me lots of rocks. All right. Let's look at these columns now. These are some of the properties that exist with logs, and they're really, really important that you know these. We're doing it for common logs, natural logs, and then logs of just random bases. So log of 1 equals 0. That's a fact. Okay. And when I say log, L-O-G, it's base what? 10. So the common log of 1 is 0. Now let's think about why that is. Take the base 10, right? That's not really showing, but it's there. 10 to what power is 1? 10 to the 0 power, right? So log base 10 of 1 is 0 because 10 to the 0 equals 1. We constantly want to be thinking both ways. Log base 10 of 1 is 0 because 10 to the 0 equals 1. Oh, that makes sense. Now, what does that mean? That means on the graph of y equals log of x, there is a point 1 comma 0, right? If you plug in a 1 for the argument, what's the output? 0. Now, is this an important point on a graph? We don't really know what the graph looks like just yet.
Yeah.
Because it lives where? Where does it live? On what?
It lives one. I mean, it lives to the right of one.
It lives to the right of 1 on the
To the right of one.
x-axis. Yeah, this is an x-intercept. This is a 0. What's log base 10 of 1? With my eyes closed. Log base 10 of 1 is what? 0. No, it's 0. Why is log base 10 of 1 0? Because 10 to the 0 is 1. Okay, let's do it again. Let's do it again with my eyes closed. What's log of 1? 0. Okay, good. Now y'all do it with y'all's eyes closed. What's log of 1? 0. We got it. See? All right. Now, what's log of 10? 1. Why is that? Because 10 to the 1 is 10, right? Remember, the log is the exponent. The log is the exponent. To what power shall we raise the base to achieve the argument? What's log base 10 of 100? Let's squeeze that in here. What's log base 10 of 100? 2. Why? Because 10 to the 2th is 100. Let's squeeze this one in here. What's log base 10 of 1,000? 3. Good, good. Because 10 to the 3rd is 1,000. What's log base 10 of 10,000? 4. You remember the whole purpose of logs? We all are agreeing on base 10. All we're looking then is at the log or the exponent as a relative indicator of the size of the number. When you're talking about base 10, it's easy to figure out what it's equal to because all you're doing is counting the number of zeros, right? On powers of 10. Now, of course, that works here because log base 10 to the 1st is 1. Look at this one. We can write this as log of 10 to the 0th power. And what's the answer? 0. Log base 10 to the 1st is 1. Another way to write 100, of course, is 10 squared. What's log base 10 of 10 squared? 2. What's another way to write 1,000? 10 cubed. Guess what log base 10 of 10 cubed is? 3. How can we write 10,000 without all those zeros? Well, that's 10 to the 4th. So guess what log base 10 of 10 to the 4th is? 4. Are y'all seeing a pattern? I hope so. If you can write the argument as a power of the base, if you can write your argument as a power of the base, the log is simply the what ponent? Exponent, right? Okay, cool, nice. So here's the summary right here. This is kind of like the distilled wisdom from what we just did. What is log of 10 to the x? It's just x, right? Now you can think about it algebraically. Put the little subscript there, remember? How are exponentiating base 10 and logging base 10 related? They're what? Inverses. When you compose two inverse functions back to back, add 5, subtract 5, multiply by 5, divide by 5, they undo each other. Look at the sequence here. If I had you evaluate this, plug in a number for x, the first thing you're going to do is exponentiate it base 10, right? Order of operations. And then you're going to take that result and log it base 10. What happens if you compose two inverse functions back to back? You're right back where you started. X marks the spot. Watch, I'll stand here. Here I am, I'm X. Ready? Exponentiate me base 10. Take that result and log it base 10. I'm right back literally where I started. There's an X on the floor where the tiles intersect. Kind of. They put the tiles down pretty quickly. There's a little gap. Oh, that makes sense, doesn't it? Okay. Now, guess what? If I take 2 steps to y'all's right and then 2 steps to the left, I'm back at X. What if I went to the left first? 2 steps to the left and then 2 steps to the right. Guess what? I'm right back where I started. So you can compose two inverse functions back to back in either order, right? Instead of multiplying by 5 and then dividing by 5, you can divide by 5 and then multiply by 5. The order doesn't matter. So guess what? Here's another thing. Not only is log base 10 of 10 to the xx, guess what 10 to the log base 10 of x is? It's x, right? They undo each other. They undo each other. We can write these two things in one line. Watch. Log base 10, I'm going to write it, of 10 to the x is x, which is the same as 10 to the log base 10 of x. The order doesn't matter. And I'm writing the 10s there as the base so that you can see the two 10s are there. Logging something base 10 and exponentiating base 10 undo each other. The order doesn't matter. So whatever you start with is what you're ending with. All right, let's look at the left side, the order of operations. Start with x. Exponentiate it base 10, 2 steps to y'all's left. Then log it base 10, 2 steps to the right. I'm back at x. On the right side, I'm starting with x, but now I'm logging it first, base 10. That's 2 steps to y'all's right first. And then I take that result and exponentiate it base 10. Now that's 2 steps back to the left. I'm right back at x, right? And that's why I'm exhausted. I'm like walking. I'm not getting anywhere, right? It's like running on a treadmill. It's like, why am I doing this? Right? I'm not getting anywhere. Yeah. The longest I ever went on a treadmill was 30 miles. And it was because we put it in the back of my brother's truck, and I sat on the treadmill while we drove to his new apartment, which was 30 miles away. Yeah. Yeah. I was smart. I knew if I just went 30 miles on the treadmill, I wouldn't even be at his apartment. I'd be right back at where we started, at his old place. 30 miles on the treadmill. Hey, let's do the same thing with base E, shall we? Base E is the what kind of log? Natural log, right? Healthier. Low, it's lower in the bad cholesterol, higher in the high density lipoproteins. Healthier, natural. My eyes are closed. What's the natural log of 1? 0. What's log base E of 1? When I say the natural log of 1, that's the same as log base E of 1, right? It's just so what is the natural log of 1? 0. So what's log base E of 1? Still 0, right? The natural log of 1 is 0 because E to the 0 power is what? 1. We talked about why any number to the 0 power other than 0 has to be 1, right? It's because anything divided by itself is 1, and the rules of exponents have to work. Okay, we talked about that. What does that mean then? That means that on the graph of y equals the natural log of x, the x-intercept is 1, 0. That's the same as the x-intercept of log base 10 of x. Those two graphs share an x-intercept. All right. What's the natural log of E? 1. What is log base E of E to the first? 1, right? What's the natural log of E squared? 2. What's the natural log of E cubed? 3. What's the natural log of the square root of E? 1/2. The natural log of the square root of E is 1/2.
Oh.
Ooh.
Log base E with a base of 2 with an exponent of E. That was very clever.
What? The natural log of the square root of E is the same as the natural log of E to the 1/2. Right? What's the natural log of E to the pink elephant? Pink elephant, right? So here's the summary. The natural log of E to the x is just x. That's all it is. Because again, we're composing these inversely. Start with x, exponentiate it base E, then turn around and log it base E, natural log. This is also is x. Start with x, now natural log it first, 2 steps to the right, and then exponentiate it base E, 2 steps to the left. So it works the same way. The natural log of E to the x is x, which is the same as E to the natural log of x. When you compose two inverse functions back to back, they undo each other, and you're left with what you started with. All right. Summary for the day. Pick any legal base now, and the legal basis for logs are the same as the legal basis for exponents. Why? because it's the same base, right? So base can be between 0 and 1. Base can be greater than 1. What is log base b of 1 for any legal base? 0, okay? Because b to the 0 is 1. B to the 0 is 1. What is log base b of b to the first for any base? 1. What's log base b of b squared? 2. What's log base b of the square root of b? 1/2. What's log base b of the cube root of b? 1/3. What's log base b of 1 over b? -1. What's log base b of 1 over b squared? -2. What's log base b of 1 over the cube root of b? -1/3. In general, log base b of b to the x is just x. If you can write the argument as a power of the base, the log is the exponent, and it works the other way around. B to the log base b of x is x. So the last thing we'll write is this. We'll combine these two, and we'll say log base b of b to the x is x, which is the same as b to the log base b of x. When you compose two functions back to back, they undo each other. Like an umbrella and a hole in a head, it's better to have it and not need it than to need it and not have it. Trepanation, that's a real thing back in the day. They would drill a hole in your head. It was called trepanation. Look it up. Ask Mr. Kilford about it. Trepanation. They thought that putting a hole in your head made the evil spirits fall, all the bad stuff would leave. Bad vibes would leave. But apparently that didn't really work. Hey, y'all have a super duper awesome, wonderful rest of your day. We'll see you tomorrow. Don't forget the worksheet is there waiting for you.